So let's go through the B3 reflections. So these are primarily probability questions with conditional and independence, and a few mixed old material as well. Like to spiral it in. So Q1, in the tree graphs, aka diagrams, such as the first question, I really had no idea where to start with the question that was given. I'm not sure where to start when information is given and which variables to multiply. Probably you mean which probabilities to multiply. I'm going to be honest on here. This was probably the hardest reflection I've done in the class so far. I felt like I didn't know what to do for each question. I definitely am going to look back on the notes and pay attention when we go over them in class. So I'm going over them now. These are feedback from last year, since you guys haven't even had a chance to start the assignment. But I figured it's helpful to have some feedback from last year. So here we go. We have a tree diagram. Mrs. Eccles chooses a student at random from the Coronado High School student body, and the following events are recorded. M is the student is male, so that would be, let me do my laser pointer right here. Pointer options. There we go. So there's male, and there's female. And then once you figure out if they're male or female, then you would go and say, oh, did you eat breakfast? Did you not eat breakfast? All right, breakfast, not breakfast. All right. So the tree diagram gives probabilities associated with these events. So find the probability that they ate breakfast given they were female. So given means we sort of change the probabilities. It's 100% that the student is female. All right. So it's no longer, we're like, oh, we know it's the person's female. All right. So what is the probability they ate breakfast? All right. So if we look at the numbers here, it looks like the probability they ate breakfast is 0.3. So there you go. Given that she ate is female. So remember, the given is the second one. It's female right there. All right. And then so this matches given a probability of eating breakfast given female. So this vertical line read as given. And given means it did happen. This trick only works, by the way, on the first branch of trees. This will not work back here. Okay, so don't change one of these to a 1. It's a nice trick here and it's very intuitive, but we can actually, if I had done it, I could have multiplied out both these probabilities and then seen how big that is compared to the total here, because I would only be looking at these. So if I had the same number there, say 0.5, right? Then I would basically say, oh, 0.5 times 0.3, 0.15, 0.5 times 0.7, 0.35, 0.15 divided by 0.35. Oh, that's about 0.3. There you go. I think I did that right. Did it in my head fast. Okay. Deanna's school bus arrives at her stop at 6 a.m. If she misses her bus, her father drives her to school. Let event B equal Deanne catches the bus, and F, Deanne makes it to her first period class on time. The tree diagram summarizes the probability in this situation. Given that Deanne makes it to her first class on time, what is the probability her father drove her to school? So the given is in the back branch, right? So you'll see I have bus and bus complement. And then I have is first class and not first class. All right, could have been better words, but okay, this will work. So first of all, we're looking for this probability. B of not catching the bus, given, so in other words, her father drove her to school, given that she made to the first class on time. So not the bus, given on time for first class. So we're going down this branch and this branch to get a specific probability, but we're going to have to adjust it a little bit. So what we do is I'm going to actually multiply out all the probabilities. So all you do is multiply straight across branches. It's not hard. Okay, here's the interesting part. There is a nice formula for this on your math chart. probability of not making the bus given their first class is on time. Is the probability of not making the bus and making the first class on time, which is this branch right here, over the probability of making the first class on time. There are only two probabilities where she makes the first class on time. So I'm going to add those two on the bottom. They're mutually exclusive because one is her taking the bus and one is her not taking the bus. So I'll just add them together. And then when I divide, I get 0.168, and there you go. There's the answer to part B. And it's to number 2. It is B. All right. Question 3. I struggle with everything, to be honest. I tried to understand why the answers, let's say 3 was 0.0064. I can't figure it out. I struggle with 3, 5, and 6. Yeah, these probabilities are tough for people. It's one of the areas where in the U.S. we struggle more than other people. So this is a very common question. You will get questions like this on your test. All bags entering a research facility are screened. 97% of the bags that contain forbidden material trigger an alarm. 15% of the bags that do not contain forbidden material also trigger the alarm. So if 1 out of every 1,000 bags entering the building contains forbidden material, what is the probability that a bag that triggers the alarm will actually contain forbidden material? So I'm looking for the probability of an alarm given it has foreign material. Well, I know that it's that probability is 0.97. So 97% of the time, foreign material will trigger an alarm. So this means that foreign material should come first on the tree because that's the given. You sort of have that number straightened out. And we'll get to the rest here in just a second. Okay, so we need to know foreign material. We know the probabilities. They say only one forbidden material, I should say. Only 1 out of 1,000 bags has forbidden material. And let me put in the numbers I know, right? We know 1 out of 1,000 bags has forbidden material. So this is going to be a very small number. And then this is the difference right here. Okay. So do you understand how I set up my tree? Okay. So the probability that you get foreign material and you trigger an alarm is 0.0097. What are we looking at? What is the probability that a bag that triggers the alarm will actually contain forbidden material? So 0.00, there's no given here. Oh, wait. The bag that triggers the alarm will actually contain foreign. So this is given that the bag triggers an alarm. What's the probability it has foreign material? So I need to look at all the alarm situations. That one too. So I'm really looking at probability of foreign material given alarm. So I could calculate these other probabilities, but I'm only interested in bags that trigger the alarm. So, and again, these are mutually exclusive. You have forbidden material and trigger an alarm, or it's a clean bag and you trigger an alarm. So this probability is that tiny one right up there. And then these two get added up on bottom. So you should see that number repeated below usually. And we get 0.0643. And here's another way to do it. So let me go back. So that's one way using the formula. Now, there are some people who really like tables, and this is much easier for them than tree diagrams. You have my permission to use tables. You just need to know how to set them up. So let me teach you how to set this up as a table. So the easiest thing to do is to come up with a grand total of bags, all right? And I said, well, it's only 1 out of 1,000 bags. Let me do 100,000 bags, all right? So if I do 1 out of 1,000 out of 100,000 bags, that gives me 100 bags. And then the rest are clean, 99,900. Then I know 97% of those bags are going to trigger the alarm, right? So 97 of 100 bags should trigger the alarm. And believe it or not, 14,985 clean bags will also trigger the alarm. Must be a pretty, 15% of bags that don't contain. That's pretty high. All right, and then we also have our no alarm, but I don't really need it because I just need to know 97 out of the total, and it's 0.00643. So there are two ways. I could have calculated these, but I didn't need them. So there are two ways to get to your answer, which is D. Number 4, 3.3% of the population are infected with a certain disease. There is a test for the disease. However, the test is not completely accurate. 94% of those who have the disease will test positive. However, 4.4% of those who do not have the disease will also test positive. This is known as a false positive. What is the probability that any given person will test positive? So first of all, we know 3.3% of the population are infected. And so probability of infection is 0.033. Infected goes first on our tree. So I'm going to put infected here and not infected there. And then we do positive, negative. So I do 0.033 and then I do 0.967, all right? And then the positive part, I get 0.94 and 0.06. So only 6% will get a negative result, but that's still kind of high. All right, and then here we actually will see 4.4% of these people test positive, but the rest will test negative. So what is the probability that any given person will test positive? So that means I just need this answer and this answer. I don't need the negatives. Voila. So I just add these two probabilities and I get 0.07358, which rounds out to D. Could I do this with a table as well? Absolutely. So here again, pick a nice large population. I'm going to go with 100,000. That typically works. And that means I would have 3,300 infected people. And so the balance would be not infected. Now I know that 94% of those are going to test positive. So I take 94% of 3,300 and I get 3,102. And I know that 4.4% of those 96,000 are going to test positive as well. You can see the number is still larger than the infected. When I add the total, 7356.8 test positive. And then I can just go ahead and say, oh, okay, divide those two numbers in the total columns. So 7356.8 divided by 100,000 is roughly 0.074. And it confirms the answer is D. On to question 5. I struggle with setting up at least probabilities that span from questions 5 through 7 and understanding what the numbers given mean in the equation. I struggle particularly with question 5. This one took me multiple tries and I do not yet understand it. I would say 15 out of 19 are not large shirts. The probability of getting the first shirt wrong is 4/5. Now there are 14 shirts and 18 total. So let's go ahead and go through this. All right. So I think the problem the first person was having is they were trying to calculate out the scenarios, but it gets a little complicated. All right. So the problem is the sales bin in a clothing store contains an assortment of t-shirts in different sizes. There's 7 small, 8 medium, and 4 large. Alan is looking for a large shirt. He starts grabbing shirts one at a time and checking the size. After he checks each shirt, he leaves it outside the bin. What is the probability that at least one of the first 4 shirts he checks is a large? So what I did is I created a tree diagram. I apparently have an early yellow on there. That's fine. Let me put the background on it so you can see it better. So the sample space of possible outcomes is 0, 1, 2, 3, or 4. So he says at least one of the first 4 shirts he checks is large. So that means if he gets 2 of the first 4 shirts, that also counts, as well as 3. So let's circle the ones that satisfy at least 4 shirts. Okay, and that would be these, right? So we're going to highlight all parts of the tree that gives us at least 1 shirt correct, large shirt. Oh, it's all of them but 1. So when you multiply out that number, oh, I thought I had an answer here. I might need to get my calculator. So you basically would multiply all these numbers out, and let's see. And then you would go 1 minus that. So let me, I'll tell you what, I'll put the calculator work in after I show it through this, because I'm going to have to record it separately. So the answer I will share shortly, but basically you take 1 minus that answer right there. Oh wait, maybe I have my math here. Oh, here we go. I have my math here. Silly me. Much easier to do the complement. Okay. So P of 0 large shirts, what is the probability of that? Well, it's 15 over 19 times 14 over 18 times 13 over 17 times 12 over 18, 0.352. That is not the correct answer. That is the complement. So I have to go 1 minus that number, and I get 0.648, which is answer A. Answer A. Question 6. I struggled a bit with number 6 because I had no idea how to find the percentile it was asking for. I'm still struggling with the style of probability questions like on questions 6 and 8. I'm just not sure how to frame the question in my head to know how to go from there. I struggle with setting up at least probabilities that span from questions 5 to 7. And let's see what we got here. According to one poll, only 8% of the public say they trust Congress. In a simple random sample of 10 people, what is the probability that at least one person trusts Congress? So your sample space is that, right? Let's circle the ones that satisfy at least one person. Oh, well, we could basically find the probabilities of getting 1 through 10 persons. But as you can see, that tree is probably pretty yucky. We don't want to do that. We'd much rather, because there are going to be 1,024 tree branches. Way too many. Way too many. We don't feel like drawing that. We could calculate the complement. 0 people out of 10 trust Congress. All right. So the complement is basically 0.92 to the 10th power, which is 0.434. So you have your first person, and we're assuming that the probability is not changing because we're doing there's a large public, and these probabilities shouldn't change for that larger group. Okay. And then, of course, you got to remember to subtract it because that's not the answer. They will give this answer as an option because you could say, I'm done, no more. But you need to go ahead and subtract from 1 and circle the correct answer, which is 0.566. Question 7. I didn't understand what a lot is, and the wording was difficult to understand. I struggle with setting up at least. So let's see. An inspection procedure at a manufacturing plant involves picking three items at random and then accepting the whole lot if at least 2 of the 3 items are in perfect condition. If, in reality, 84% of the whole lot are perfect, what is the probability the lot will be accepted? So there are only 3 items. I can do this tree because it's like perfect, not perfect, right? So it's 2 to the 3rd. I'm going to have 8 branches. So there's your tree. And so this lot would be accepted. And so with this one, and this one, and that one. And so I just basically add up these probabilities here. So it'd be 0.84, 0.84, 0.84. So let me show you. There's my numbers, right? And then I have to fill in the 0.16, 0.16 there, 0.84. 0.16, 0.16, 0.84. So once you multiply all these numbers out, right, then that should give you, so we're going to multiply them out and add them up. All right. And you get the 0.931. There you go. So tree diagrams, some of you fight these, you're kicking and screaming. We have to drag you kicking and screaming to draw a tree diagram. They're so useful. Just come over to the dark side. Use the tree diagrams. It's so much easier. All right. Question 8. I struggle with identifying IQR. So let's see what 8 said. Below is a stem plot of the weights of a random sample of 18 adult Maine Coon cats. Which one of the following statements must be true about the distribution? So we know the median is the midway point. If there are 18 coon cats, that means the midpoint's between points 9 and 10. So the median is 17.5. Once I find the median, I can find Q1 and Q3. So Q, by the way, skew right. It is skewed right. So the mean is greater than the median. We're pretty sure. You're never 100%. It can blow your mind sometimes. But we're pretty sure that it's to the right of the median. 13 pounds is definitely below average, right? And they said must be true. So we're saying 13 pounds is definitely below average because the median is 17.5 pounds. So we're very confident that it's probably C. Let's continue on. I went ahead and took advantage and put the data into Staplin. And you can see the mean is actually 18.22 pounds, which as we predicted is greater than the median. All right. And then you can see the summary stats. 14 and 21 are the Q1 and the Q3. So we could figure out the IQR. Under the 1.5 rule, the IQR 30-pound cat is an outlier. Probably not, because 14, 21, that's 7, 10.5 plus 21 is greater than 30. So we know D is not correct. We know the mean weight is not lower. We know the 20-pound cat's not the median. And standard deviation is less than 10. Well, shoot, it's at least 10. Sorry. I can see from the summary statistics. So the correct answer on this one is C. Number 9, a smash or a hit. Researchers asked 150 subjects to recall the details of a car accident they watched on video. 50 subjects were randomly assigned to be asked about how fast were the cars going when they smashed into each other. For another 50 randomly assigned subjects, the words smashed into were replaced with hit. So how fast were the cars going when they hit each other? The remaining 50 subjects, the control group, were not asked to estimate the speed. Then a week later, all subjects were asked if they saw any broken glass at the accident. By the way, there wasn't any. The table shows each group's response to the broken glass question. So what proportion of subjects were given the control treatment? Well, you just have 50. So total on control treatment out of 150. That's your grand total, right? They told you there are 150 subjects. So that's 1/3, also known as 0.333. Okay. Number 10. What is the marginal relative frequency for the subjects in the study who said yes? So we only have, they either said yes or no, but it's not 50-50. Let's look. So we have a total here of 29 said yes. All right. And then we take that 29 and divide it by 150, and we get 0.1933, which is probably close enough to be 0.1930. Okay. Number 11. What percent of subjects were given the smashed into treatment and said they saw broken glass at the accident? So we're looking at what percent of subjects, total subjects, saw the smashed into treatment and said they saw broken glass. So there were only 16 of those. So 16 out of 150. So it's yes and smashed into. There is no given here. Be very careful. Understand the difference between your ands and your givens. So that works out to 107. So the answer is B. What proportion of subjects who said they saw broken glass at the accident received the hit treatment? So now we're saying only people who saw the broken glass, so that would be the yes row, received the hit treatment. So how many received hit? So we had 29 total who saw broken glass. Here's the hit column, but I only need that 7. So I'm going to take 7 over 29, which turns into 0.241. The answer is D. Number 13. What percent of subjects who received the smashed into treatment said they did not see broken glass at the accident? So we're looking at smashed into, and then that's 50 total, which makes sense because they had 50 randomly assigned to each group. And how many of those said no? That was 34 out of 50, also known as 68%, right there. Okay, Then we have 14. Which of the following choices gives the distribution of responses about whether there was broken glass at the accident for each of the groups? So I'm just going to do the yeses because the no's are, the balance remainder. Okay. So we still have what we sort of talked about. The smashed into was 50. And then we said smashed into. This time I'm using the top number. 16 out of 50 is 0.32. And you can see this one right here still matches because it's got 32 and 68%. So I'm leaning towards A. All right. Then I do the hit. 7 out of 50, 14. And so the rest, 86%, would be no. And then finally the control. 8 out of 50 would be 16%. And wait, did I misdo that? Oh, I have a typo. This happens. 10, 6. Make that a 6, not an 8. All right, so that's 0.12. 0.12. Sorry. There you go. Easy to make mistakes on these. Pay close attention. All right, and so your answer is A, all is right with the world. On to problem 15. Does the graph reveal an association between the response about broken glass at the accident and the treatment received for the subjects in the study? Why or why not? So this is a segmented bar graph, which in my opinion is the top choice for checking association between categorical variables. Now, mosaic is a close second on that one. So this is when you're just comparing groups and you don't care which group is the biggest. All right. That's why we like to do relative frequency. We do not like to do absolute counts. I had to ding some of you on your test because you gave me absolute counts and side-by-side bar graphs that did not have relative frequencies on it. Don't do that. So, is there a difference in relative frequencies of yes for the different categories? If so, then there is an association. And I can see that the probability someone said yes, which is the dark one, given they were smashed into, is definitely not the same as yes, given they said hit or control. So we're going to definitely say yes, all right? And that would be, the graph reveals an association because knowing which treatment a subject receives helps us to predict whether they will respond that they saw broken glass at the accident. Last question. What measures can be taken, especially when restoring wooden buildings, to help wood surfaces resist weathering? In a study of this question, researchers prepared wood panels and then exposed them to the weather. Some of the variables recorded were type of wood, yellow, poplar, pine and cedar, type of water repellent, solvent-based, water-based, paint thickness in millimeters, and paint color, white, gray, light blue, and weathering time in months. Which of the following is a true statement? So, type of water is quantitative. No, that's not. Type is not quantitative. It's categorical, right? Paint color is also categorical. Don't know why that came next. Time is quantitative. That's likely our answer. And wood type is categorical. Paint thickness is quantitative. So the only one that matches is C. And that's it for your problems. Hope that helped clear up some issues you might have while working on these.